Hi, this is Jack Jackson. This is the first video in this last playlist from the History of Mathematics, playlist 13. And in this video, we're going to be talking about the more recent mathematics, mathematics from the 20th century through well, to date, the first part of the 21st century. Um, I have several sources. A couple of them are the History of Mathematics by Carl Boyer, History of Mathematics and Introduction by Victor Katz, and MacTutor History of Mathematics, and maybe some other sources for what we're going to be talking about here in this video. So this particular video, we're going to just start by giving you an overview of some of the mathematics from 1900 to date. Actually, before we do that, let's just do a quick recap. Some of the major mathematical advances prior to the 20th and 21st centuries. So in the 17th century, notation had become more standardized, work on the theory of prime numbers had taken place. We had the development of analytic geometry, the beginnings of probability theory, and probably most significantly, the discovery or creation and development of calculus. Major mathematicians of the 17th century included René Descartes, Blaise Pascal, Christian Huygens, uh, Gerard Descartes, Johannes Kepler, James Gregory, Isaac Barrow, Gottfried Leibniz, Jacob Bernoulli, and Sir Isaac Newton. As we move into the 18th century, the 1700s, we see really the establishment of the modern age of mathematics. At this point, the growth of mathematics really started taking off. Modern notations had become standardized, at least prior to that or during that century. Extensions of the techniques of calculus dominated a lot of the work in that century. We had our first calculus textbooks. Trigonometric functions were introduced into calculus. We had infinite series, differential equations, and calculus of variations as applications and further work with calculus, including differential geometry. Applications of calculus spurred many advances in physical sciences such as astronomy, optics, heat transfer, electricity, fluid dynamics, and others. The metric system was developed by the end of the century. The first steps were made towards abstract algebra, but we really didn't quite have full abstract algebra yet. We saw growth in the theory of probability and some initial applications of statistics, including establishment of the least squares regression techniques. Right at the end of the century, we have the fundamental theorem of algebra being proved by Carl Gauss, and there's some work on the parallel postulate in geometry, but not yet non-Euclidean geometry. We have a little bit of the birth of graph theory with the work of Euler, and of course the scientific method by this time had been really established as a way we look at science, and in general this idea that mathematics and science gave a rational way to explain the universe and to solve problems. Some of the major mathematicians of the 18th century include Johann, Daniel, and the rest of the Bernoulli family. Euler, D'Alembert, uh, Lagrange, Monge, Laplace, Legendre, Lambert, Sacchari, Maclaurin, Agassi, and Carl Gauss being a giant there at the end of that century and on into the next century. So we get to the 1800s and 19th century. This is where we have really the golden age of mathematical rigor. We have, once again, an accelerated growth of mathematics. The 19th century more than doubled what was known about mathematics. You take all the mathematics from antiquity uh, up to 1800, and then you look at what happened between 1800 and 1900, and there's more math done between 1800 and 1900 than all of the math before that. One of the big things that was worked on during that century was the rigorous foundations of calculus were established, but also entirely new areas of mathematics were created or at least started. Real and complex analysis were started there. some initial work with abstract algebra, at least some fledgling work there with groups, rings, and fields. Galois theory was getting a start there. Also, same work with linear algebra. The first part of set theory was starting to show up there, and non-Euclidean geometry was discovered, which was an earth-shattering way of looking at the world, and it really shook the foundations of what was going on with mathematics. And now the mathematicians start to look at things more abstractly and trying to be more conscious of the foundations of things. Projective geometry, graph theory, topology, probability statistics, logic, and a spectacular rising growth in technology happened during the 18th century. If you start at the beginning of the 18th century, many things were not. At the end of the 18th century, about 1800, a lot of life was very much like it was a millennia before. However, by the end of the century, you had a lot of things that nobody saw coming: steam engines, electricity, even machines, uh, powered boats and trains and all kinds of different cars, even earliest cars and so forth. So you had lots of all kinds of transformations, a light bulb, all kinds of things that happened during that century that people didn't even see coming. It really changed the way the world worked. Some of the major mathematicians, uh, Carl Gauss did a lot of his best work during the 19th century. Cauchy was another giant, probably in some ways the most influential of the bunch. Dirichlet, Riemann, Weierstrass, Kovalevsky, Dedekind, Cantor, Germain, Abel, Galois, Cayley, Hamilton, Boole, Bolyai, Lobachevsky, Klein, and Hilbert are some of the ones that we mentioned in our videos before, talking about mathematicians of the 19th century. The last couple here, Felix Klein and David Hilbert, did a lot of their best work on into the 20th century as well. So if you look at this, kind of sets the stage for what happened in the 20th century and beyond. So once we moved into the 20th century, from 1900 to on to the present in the 21st century, we see an even further accelerated growth of mathematics. And again, we've more than doubled what the known mathematics. The 20th century more than doubled uh, the mathematics was known today. In other words, there's more in the 20th century than ever been before, and it's even growing faster in the 21st century. Along with this, known mathematics had expanded so much that it's now practically impossible for any one mathematician to have even read all the published mathematical results, much less have mastered all known mathematics. While Poincaré and Hilbert may have come close, no one really since Gauss has had a nearly complete mastery of the mathematics known at the time. Though studying mathematics and the various sciences and engineering were increasingly separate sets of people. If you look back in the 1600s, 1700s, even the 1800s, uh, the top scientists of the day were also the top mathematicians and vice versa. There wasn't really a separate thing. Not, in fact, a lot of times they wouldn't have considered themselves a mathematician or a scientist. In fact, for a long time they were just called natural philosophers, for example. But increasingly, uh, scientists work on science, math works on math, engineering works on engineering, and there's obviously some overlap and definitely some different sharing of skills. There's certainly things like mathematical physicists that are heavily both mathematics and physics, but in general, people become more and more specialized. And even within mathematics, the days of the mathematical generalist working on all areas of mathematics was gone by the 20th century. Um, Hilbert may have been the very last one that really just tried to do lots and lots of major areas. So nowadays, research mathematicians specialize in more restricted areas, with typical mathematics research going further and deeper in specific fields, but usually with a specific mathematician not working outside of a few narrow fields. a few exceptions to this where people can do a lot of different fields, but even those folks don't try to do everything. They pick a few fields to work on. And even though they're, on the other hand, their training as an undergraduate and graduate school uh, includes broad areas of mathematics, and some of those were completely unknown even to the most advanced mathematicians just 100 years prior. So, in some sense, the best mathematicians of today know more mathematics than the best mathematicians of 100 or 200, 300 years ago. Mathematics, of course, why? Well, it's because earlier folks had created that mathematics, and we now know it. Mathematics became a major profession with universities producing thousands of new PhDs and hiring many of them to teach and do research and thus creating new mathematics every day. Universities solidified their position as a major employer of research mathematics, although significant numbers of research mathematicians are also hired by private and corporate labs and think tanks and so forth, and by governments. One of the largest employers of research mathematicians in the world is the National Security Administration of the U.S. federal government. So, of course, the NSA doesn't always publish some of the things because of national security, but they're doing some cutting edge applied mathematical research there too. Mathematics education underwent numerous reforms and became, and education in general underwent a lot of reforms, but especially math education. And mathematics is now a core portion of a public school education. We actually now have public school education in most developed countries anyway. And mathematics is a big part of that. And that's also a big employer of mathematicians as mathematics educators in public school and in universities. During the last half of the 20th century, universities in the United States took their place along the greatest universities in the world in training and employing some of the top research mathematicians in the world. Really, when you looked at the 19th century, if you wanted to look at the best place to go get a mathematics education and where the best mathematics research was going, you're going to look at the great European universities. Uh, you know, uh, Cambridge and Oxford in England and Göttingen and Berlin and Germany and some of the places in Paris and different places like that in Europe. We had some important schools in the United States, but it took some time. And if you did have a great mathematician there, oftentimes they were an immigrant from Europe, or at least had their training in Europe. That became increasingly less so as you get to especially the second half of the 20th century, really after World War II. Um, the U.S. starts producing some of the best mathematicians in the world in our universities there as well. Uh, Not saying that they've dominated the world, but they took their place along with everyone else. The U.S. is now a destination spot for many foreign um, students who want to study mathematics here. Business, industry, and government also hire a significant number of mathematicians, and they apply mathematical skills to a wide variety of practical matters. But in addition to that, mathematics is used as an incredibly powerful set of tools by those who would not consider themselves mathematicians, but who are actually, in fact, mathematics practitioners, scientists, engineers, and many others, using mathematics to solve problems and make progress in an astoundingly wide variety of endeavors. One of the most striking results of the uses of applied mathematics is a staggering growth in technology from 1900 to the present. I already mentioned how the 19th century saw an unprecedented growth, and so by the 20th century, we probably expected to see fantastic growth. But some just amazing things have happened. Just to give you an example, at the beginning of the 20th century, no one had ever even taken a powered flight. Now, there were some air balloons, uh, hot air balloons that were lighter than air flight, but no heavier than aircraft had ever been flown. But the Wright brothers take their very first brief flight in a heavier than air vehicle in 1903. Yet only in 1969, two American astronauts walked on the moon. What an incredible progress in only 66 years. That's absolutely amazing. that we can go from not being able to fly at all to walking on the moon in, less than 70 years. Mathematicians were the first computer scientists, creating software and hardware of the earliest computers. The father of modern computing is Alan Turing. He created the first electronic programmable computer during World War II to crack the Enigma code of Nazi Germany. He is single handedly responsible for shortening the war and saving hundreds of thousands of lives and helping win it for the Allies. During the last 80 years or so since that time, computer technology has grown to the point that nearly everyone in the U.S. has a computer in their pocket, their cell phone, which is connected to a global information network where we can instantly retrieve all kinds of information, perform some computations on that, and communicate instantaneously worldwide. Computers are also in all kinds of devices, not only in phones, but also household appliances and automobiles and all kinds of things. Prior to the 20th century, it took weeks or months for information to be transmitted from one continent to another. Today, emailing, texting, cell phones, etc., along with the internet, make it possible to access information from anywhere, to communicate instantaneously, and to allow for collaborations and exchange of ideas across the globe. Mathematics advances have become global and somewhat decentralized. There are important mathematicians today from nearly every country in the world, with advances in many fields of pure and applied mathematics being accomplished worldwide. Mathematics has become a universal language. Sharing mathematical knowledge and achievements through publication in peer-reviewed journals has become the academic standard, and sharing rather than hoarding knowledge is rewarded. So contrast that with what we had studied earlier about how much competition there was to find a solution to the uh, cubic polynomial equations and what kind of conflict that did, or the conflict that arose between Leibniz and Newton. Had all these folks been encouraged to publish their works right away, uh, there wouldn't have been these as big of fights. Things would have moved forward a lot faster. And this is a much better thing that we have today. Um, Certainly, there's still um, competition, but we have a lot more cooperation as well. The fields of probability and statistics grew greatly in the last 1.25 centuries, so that statistics are now everywhere. Statistical techniques are used in nearly every field of research, from the physical sciences to social sciences to business to politics and beyond. One really needs to understand some basic statistics in order to be able to correctly understand even basic news stories. I would say that a basic statistics class uh, should be required pretty much of everybody. It should be the basic general education class, because it's so pervasive in its utility to everyday folks in all kinds of situations. Statistics, calculus, and many other areas of mathematics have become powerful tools for application in an astounding number of different ways. But expansion of pure mathematics has also exploded since 1900, not just applied mathematics. David Hilbert is generally considered the most influential mathematician of the late 19th to the early 20th century. In 1898, just before the beginning of the 20th century, he published his treatment of Euclidean geometry. This work went back to the work of Euclid and other ancient Greek geometers and carefully fixed their work to make explicit all assumed postulates. Then he carefully provided modern synthetic proofs of basic Euclidean geometry results. He was able to do this in part because of the groundbreaking work in geometry, including non-Euclidean geometries, that had taken place in the 19th century. So the century began by going all the way back to the classical ancient Greek geometry where we started, where a serious study of mathematics began. And Hilbert's approach is the basis for the current approaches to Euclidean geometry. Klein and Hilbert continued to work on geometry into the early 20th century. They also worked with expanding the understanding of various non-Euclidean geometries. Later mathematicians worked with finite geometries, projective geometries, dual geometries, and other new non-Euclidean geometries, and even found some new theorems in old Euclidean geometry as well. In 1900, Hilbert started the new century by publishing a group of 23 important problems or areas of research in mathematics which he thought should guide the next century or more of pure mathematical research. Some of these problems have since been solved, but others remain open and are continuing to spur ongoing research to this day. A similar group of 7 problems was published in 2000 to start the new millennium, and they were designed to inspire the highest levels of research in the 21st century and beyond. The Clay Institute has guaranteed a $1 million prize to anyone who can provide a verified solution to one of them. To date, of the 7, only one of the 7 millennial problems has been solved. Research in pure mathematics from 1900 to present has continued and expanded the trend of the growth in mathematics in the 1800s. Abstract algebra, real analysis, complex analysis, set theory, and graph theory were all started in the 19th century, but they each took off as important areas of mathematical research in the 20th century forward. Topology really got its start in the 20th century, although there's some precursors of it before. Abstract algebra, real analysis, complex analysis, and topology are considered core subjects for graduate study in mathematics, with introductory courses in these areas being commonly required for many undergraduate mathematics majors. For example, in my PhD in pure mathematics, we had to take exams. We had to take a two semester sequence of courses in all 4 of these areas and take exams and uh, qualifying for our preliminary exams to pass all those before we could continue in the program. Each of these areas have advanced to the point that they have numerous sub-areas of even more specialized research. For example, within abstract algebra, groups, rings, fields, and linear algebra all have active research areas. Foundations of mathematics were also examined, including set theory and axiomatic treatment of the natural numbers, infinite and transfinite numbers, and more. Mathematicians looked for ways to further generalize the mathematics of earlier periods. Category theory was created to examine the most abstract levels of mathematics, sort of the foundation of everything. While there is still plenty of competition to establish priority and publication of important mathematical ideas, mathematicians often collaborate on increasingly difficult problems. Now, I want to lift up one example that I think is kind of remarkable. My PhD was in finite group theory, at least my research was. So I'm going to talk about an example from that. In group theory, a simple group is a group whose only subgroups are the trivial subgroups of the identity subgroup and the original group itself. Non-simple groups can be decomposed into smaller parts, but not simple groups. So simple groups can be thought of as the building blocks for all groups. So one natural question is, well, what are all these simple groups? So one example is the only non-abelian examples are simple groups of simple groups are the groups of prime order, which are actually cyclic, being powers of a single generating element. There are infinitely many primes, so there are infinitely groups in this class. Now, there are just a few such classes of finite simple groups, and they were found in the early 20th century. And there were a few simple groups that were known from even previous century that did not fit into one of these classes. And at that point, it was not known what the complete list of finite simple groups was, say by the mid 20th century. So a concentrated effort was undertaken by top group theorists to find and classify all the finite simple groups. They were ultimately able to succeed in this endeavor by the late 20th century. We now know that in addition to a few classes, each one of which has infinitely many simple groups in it, like the groups of prime order, but there's only just a few of those classes. There are additionally 23 sporadic groups which do not fall into the other classes. The biggest one of these is called the monster group, which has an incredible number of elements in it. You could look that up if you're interested. The proof of this classification of finite simple groups theorem spans hundreds of pages and is spread out through multiple journals with portions proved by various mathematicians. So this is a remarkable accomplishment, and it's a testament to the power of cooperation and sharing of ideas. Near the very end of the 20th century, Andrew Wiles finally produced a proof of Fermat's last theorem. Fermat's last theorem was x to the n plus y to the n equals z to the n, for n is a specific natural number, has no solution for x, y, and z where they're uh, integers if n is at least 3. Now we know if n is 2, there are lots of solutions like 3, 4, 5, the other Pythagorean triples. But some work had been done on this. Fermat wrote in the margin, "Oh, I have a remarkable proof of this," but he never actually provided the proof. Well, this spurred on lots of interest in this problem. Uh, Euler had made some progress on proving a couple cases, but had sit there and nobody had been able to actually produce a proof of this for a long time. So this is a theorem from the 17th century, and it work on this problem, even though it's simply stated, actually had created a lot of significant mathematics. And so finally, we got an accepted proof that was provided several hundred years later. Often, an earlier unsolved problem can lead to entirely new areas of mathematics. We should note that throughout much of the history of mathematics, women were actively discouraged from pursuing serious mathematical study. In spite of this, we have seen that several women were able to overcome these odds and take their place among the best mathematicians of all times. Perhaps the best of these was Emmy Noether, who was a giant in the development of abstract algebra in the early years of the 20th century. I would place her among the greatest mathematicians of all time. Fortunately, the situation for women in mathematics has dramatically improved, especially in the last half century or so. Perhaps not as far as it should still, but we're making great strides there. Women are finally taking their rightful place among mathematicians at all levels, including at the very top, with females being awarded the mathematics' highest awards, the Abel Prize and the Fields Medal. I think this is one of the most significant advances in mathematics since 1900. We're effectively doubling the potential pool of contributors to mathematics. The number of important mathematicians from 1900 to date is so large that it's impossible to list all of them in a playlist such as this. And so I'm not going to make any attempt to do that, but I will be making somewhat arbitrary choices of a few of the interesting mathematicians and telling a little bit about them and their contributions as we proceed through the playlist. And my apologies to the many other equally deserving folks. We now have a significant ongoing research from mathematicians of all genders, all countries, all ethnicities. There is truly a global community of mathematicians. Mathematics continues to include several active areas of research, with new mathematics being created every single day.